All right, in the last video, we ended with understanding how we use matrix notation to describe a linear programming problem in this shorthand format. So all you really need to know about this is how to translate this symbology into practical terms. So when we see this z equals c transpose x, what we're really saying is that's just shorthand for our objective function. Z is the value, and then the function is the numbers c1 times x1, c2 times x2, all the way up to c subscript n times x subscript n. If there are n variables, all the numbers c1, 2, and so on are just the coefficients of our objective function, and all the symbols x1, x2, and up to xn, those are just the variables of our problem. So far we've been focusing on problems with small numbers of variables to keep things simple, but in reality problems have a lot of variables and a lot of constraints, but the interpretation doesn't change. So that's just our objective function. The symbols we write here, ax less than or equal to b, again, is not a proper mathematical notation, it's just a shorthand notation. You can't say one matrix is less than or equal to another in a normal way, but we define it to mean that each entry of one matrix is less than or equal to the corresponding entry of the other matrix. So again, if we have m constraints in our problem and n variables, then we have a matrix A which has m rows and n columns. And then we have m constraint inequalities. For each of those, what this ax less than or b is saying is that each row of A gives us the numbers to multiply by our variables to create one of the constraint inequalities, and the numbers in B are the right-hand side of those inequalities. So the first constraint would be plugging in I equals 1. So you would take the numbers from the first row of A, and you take the first number from B and create this inequality. If you wanted the second constraint, you take the numbers from the second row of A, and the number that's the second number from B. And the whole reason for doing this is to understand what's called duality and dual problems. Every linear programming problem has a related problem called the dual problem. What we're going to see is both of these problems, if either one of them has a solution, they both have a solution, and their solutions are connected. So basically solving one of the problems actually solves both. And since our linear programming algorithms generally deal with maximization problems, that's okay, because the dual of a minimization problem is a maximization problem. So in terms of computer programming, we really only need to know how to solve maximization problems, because when we have a minimization problem, we just translate it into its dual problem, throw it into the computer, and then interpret what that means in terms of the original problem. So the first skill we need is just basic idea of translating problems to and from matrix format. So that's the first basic skill you need, and it's just about copying and pasting things in the right manner. So for this maximization problem on the left, I want to think about it as this general matrix form on the right. So I just have to translate. So C is the matrix of numbers that appear in the objective function. So 5, 7, and 3. So I write 5, 7, and 3. We generally think of C and B and X as columns, not rows. But for putting things on paper or into a document, it's easier to save space and write them as rows, and then just put a T for transpose to say it's really the column. So C is really the column, the numbers going from top to bottom, 5, 7, 3. B is the right-hand side numbers of our two constraints. So it's a matrix that has two entries, 5 and 4. Again, we write it as a row, but then we put a T to make it a column. And we have three variables, x1, x2, and x3. So our variable matrix x in boldface is just the matrix that stores our variables x1, 2, and 3. And then our matrix A is the matrix of all numbers appearing in all of our constraint inequalities. So the first row of A are just the numbers in our first constraint. So it's 2 times x1 plus 0 times x2 plus 1 times x3. So that's why we see 2, 0, 1 in the first row of A. And then for the second constraint, we have a 1, 1, and a negative 3 being multiplied by our three variables. So we put those numbers in the second row of A. Again, the interpretation is if you actually multiply this matrix A times the column x1, 2, and 3, what you get is a matrix that has two entries. It's a column. The first entry is the left side of the first constraint. The second entry is the left side of the second constraint. Keep in mind, those are just numbers. We just haven't plugged in values for the variables yet. So we're saying each of those numbers has to be less than or equal to the corresponding numbers from B, 5 and 4. So be able to translate a problem from the format on the right, on left, into matrix format, just so that we can translate the problem into its dual problem much easier. So what is the dual problem? For every maximization problem, there's a dual problem. Now we are focusing on a very specific type of problem. Our problems have constraint inequalities which are always of the less than or equal to type if it's a maximization problem. And all the variables are non-negative. The non-negativity is the most common restriction for a linear programming problem. Most problems in the real world will have this constraint. So it's reasonable to restrict ourselves to this kind of problem. Also, if you have a maximization problem which has some inequalities which are greater than or equal to, you can always multiply them through by a -1 and make them into a less than or equal to inequality. So in a sense, we can always reduce most problems to this format if it's a maximization problem. Now, the minimization problems have the other form. They'll have greater than or equal to inequalities. So we call this first problem, this maximization problem, we call it the original or primal problem. You'll see different words used for this. The dual problem of this maximization problem is obtained by simply creating this minimization problem below. What we have to do is introduce new variables. We're calling them U. And what we're doing is we're replacing the roles of our C and B in our original problem. So B now becomes the coefficients of our new objective function, which we're trying to minimize, and C becomes the right-hand side of our constraint inequalities. So we're basically flipping things around, which is exactly what transposition does. I have a capital T here, so there's a typo. I'm just going to make that a lowercase t. This is just A transpose. So by doing all this flipping around, we really just have to flip our matrix around, make the rows into columns. And the reason for this to make sense is if X has n numbers in it, and B has m numbers in it, then when we swap the roles of B and C, we have to swap the rows and columns of A and to make things match up and make sense. So if X has, say, 10 variables, and we have 5 constraints in our original problem, our new problem will have 5 variables and 10 constraints. Now the variables U are new. They're distinct from our X variables, our original problem. However, we will be able to interpret them as closely related to the slack variables we introduce in our original problem. So interpreting the dual problem is not easy to understand. And it takes some independent thought on your time, just to take some time and really think about it. Take a specific example of a word problem that we've done, maximization problem, especially one that's maximizing, say, a profit. That's really the kind of problem to focus on. So if we're maximizing a profit, subject to some constraints, then we can imagine that each of our variables is the number of units of some product I that we're going to choose to produce in order to maximize our profit. All right, Z, which is the C transpose X. So our variables in the new problem, the dual problem, what these are is these are related to profit because C is in dollars. So the units of A transpose U has to be in dollars. But we already know what the units of the numbers in the matrix A are. They're related to resources and each of our products. So the jth variable of our dual problem is basically profit per unit of resource Bj that's used. So once we solve the problem and we know how many of each resource we've used, we can basically figure out how much profit was obtained by each use of each unit of each resource. And that's basically what Uj is. So why do we want to minimize this B transpose U if our goal in the original problem is to maximize profit? The idea is by minimizing this quantity, we're basically finding the most efficient way to distribute our profits among as many used resources as possible. Remember, in the original problem, we would like to use up as many resources as we have available. So we want to use up as many as we can. So the more resources we use, the more the profit is dispersed amongst each unit of resource that we're using. So we're minimizing that quantity. So that's why we want to minimize this quantity in the dual problem. Now what actually happens is actually kind of nice. When you solve either of these problems, the value of the objective functions, the minimum of the dual problem, and the maximum of the original problem will have the same value. So there's the connection. These two will have the same value. And because it's really because of this interpretation that we have here. And just to see that duality goes both ways. So if I have a minimization problem of this form on the right, its dual is the problem on the left. So for each maximization problem, there's a unique dual problem. And for each minimization problem, there's a unique dual problem. And to see this, it's actually not that difficult. If we take our minimization problem, we can always change it to a maximization problem by just multiplying everything by -1. Notice that I just took my objective function of the dual problem and I multiplied it by a -1. So if I want to minimize a bunch of numbers, that's the same thing as maximizing their negatives. And if I multiply a greater than or equal to constraint by a -1 on both sides, I get a less than or equal to constraint. So converting the dual problem into a maximization problem by multiplying by -1 makes sense. And then we say, what's the dual of a maximization problem? Well, it's the minimization problem of this form. But now I can just undo the minus signs and turn this back into our original maximization problem. So that just kind of illustrates how the dual problems go hand in hand. There's only one dual problem for each problem.